And welcome back. Now let's talk about the next big piece in our logic design puzzle, the transistor. So the transistor was born 2 days before Christmas, 1947, just a couple of years after the war ended. Boy, it fundamentally transformed everything we know about electronics and all the hardware devices you have. give its due to the fact that they invented this transistor back then. It was huge. It was this big. The goal was to try to figure out what was happening. They fully didn't understand what was happening in the early days. If you look at the story, there's a whole, I linked on the top right a couple of videos, and I encourage you to watch pbs.org/transistor for the history. They were like discovering this wonderful piece of science that like current can flow. It's called a semiconductor because current flows and is even amplified in this wonderful way if the distance between these two leads is just right. So they had to take a razor blade and cut them. Watch that video. It's a fascinating video. But the idea is it's called a semiconductor for a reason. Sometimes it conducts, sometimes it doesn't. And you can control whether it conducts electricity or not with another source. So it's like one source acts like the gate to tell you whether these two leads are are either amplified, the voltage here is either amplified or either connected or not connected. So it can either use as an amplifier or as a switcher as well. I want to give credit to Burdeen, Shockley, and Bertin as the inventors of this back in the day. Before that, they had vacuum tubes, which were, thousands of times the size and would break and fail at unexpected times. And it was really hard just replacing the vacuum tubes and all the electronics before the transistor came in. So it also had better life, better longevity for them. After that, integrated circuits, shrinking the size of these things. Every year we see the size of transistors shrink. It's really remarkable what they're able to do in today's computer engineering. So it's incredible. You build these things in networks. Modern digital systems use CMOS. CMOS stands for complementary metal oxide semiconductor. So this is the technology used, and they use as a voltage control switches. So we're going to continue on the idea of a switch. We saw it in the last lecture with the idea that could you make this transistor be a switch? I'm not going to talk about amplifiers in the analog domain, just a switch. So here's a picture. A transistor is usually a 3-lead device, and you can tell whether it's going to be used as an amplifier or not, whether it has a heat sink on it, because these things get hot. So if it's a big one that you're going to use, if it has a big heat sink on it, probably it's used as an amplifier, and that heat sink is being used to dissipate that heat. If it's not, if it's a smaller one, if you go to the electronics store and you buy a smaller one that doesn't have a heat sink, probably it's used as a switcher device, or as a low-level amplifier. Here's the idea. You got 3 leads, drain, gate, and source. How do you remember those 3 names? DGS. Well, Dan Garcia says drain, gate, and source. And here's the idea. Source has potential. I have this water and I want to be able to flow to the drain, but I can't there because there's a gate preventing it. And that's the idea. It's a voltage controlled gate. That's the big idea here. So as I get my pen, let me just show you here. Here's my source. I want to be able to send current to the drain. I'm going to pour it into the drain. It's too heavy. I got all this current, got all this potential, got to pour it down, got to get some current flowing so I can pour this potential into the drain. But my gate's saying, hold on. My gate controls it so that when the gate's voltage is higher than the source voltage, this thing closes, and there's a path, okay? So only when this gate voltage goes above a certain threshold, which is epsilon above the source voltage, then that closes the switch, and now there's a path and current flows and everybody's happy, okay? Closed circuit. This is called an N-channel transistor, and I think of N as a normal. That's the normal way of thinking about it, okay? P, which has a circle, is the opposite, okay? This is kind of like a complementary side of this. So P is the opposite. When you have high voltage, when the gate voltage is bigger than the source voltage, then it opens. So normally it closes. The gate, current goes, the voltage goes high, it closes the circuit. This is exactly the opposite. Current goes high, it opens the circuit. Okay, so let's actually see a little animation of this. So here we go. So G is low. So my gate voltage is low. Therefore, the N-channel transistor is open. The P-channel transistor is closed. And when the gate voltage is high, the opposite happens. I close the gate in the N channel and I open the gate in the P channel. Okay, remember that because we're going to use it in one slide. You guys ready? And action. Okay, I built a circuit. This is pretty cool. I've got a voltage source. well, 3 volts, we'll call it 1. We call it a digital 1, okay? And I've got ground, like into the ground, no potential ground. I can put a wire into the ground, that's ground. And that's 0 volts. So I've got a Y out here, and Y needs a value. Now, if I disconnect Y has no value. It isn't either 0 or 3 volts. It's just floating in the air. We can't have that. So we always have to have our Y have one connection, either to 0 or 3. That's part 1. And part 2 is Y there can't ever be a short circuit. I can't ever have a path from 3 volts, from a 1 to a 0 without going through a resistor. That's going to be bad. That would be like shorting out something. You don't want to short that out. So there has to also be never a connection in these circuits between 3 volts and 0 volts, or from a 1 to a 0. Remember those two things, okay? Output has to have at least something driving it. That's 1. And 2, you can never short circuit high to ground, okay? Power to ground. All right, here we go. What's the relationship, though, between X and Y? Here's a beautiful circuit, okay? So when it's 3 volts, I'm drawing this picture here, 3 volts. Remember, this is the N-type down here, there's the normal type, and here's the P-type. You remember from the circle. So let's think about this. Here we go. Well, when I've got 0 volts, okay, when X is 0, X is low, okay? 0 volts means X is low, okay? X is low, that means this closes. The P-type closes. This is a connection. Now I've made a little wire, like it goes up and down, it goes across. There is the gate has been closed there. But we saw that before, an N-type, it's an open switch. Okay, well, then is there a connection from 3 volts to 0? No, okay? Because this is an open circuit, that means there's no way that this 3 volts, who's gonna go 3 volts, 3 volts, 3 volts, Y gets 3 volts, and then sees this open circuit doesn't go to 0. So that's good so far. So when I put X is 0 volts, when X is low, Y is high. They go low, you go high. Huh? See how I did that with the Michelle Obama? Okay. Now, next, what happens when X goes high? You say, well, Michelle, does that mean when they go high, we go low? Is that what that means? Well, let's see. Let's see what happens here. So X goes high, okay? Well, that means this is going to open. And then this is going to close. And then when that closes, what's Y? Does Y have a value? Yes, it is. It's connected directly to 0 through that path, and it is disconnected from 3 volts. So Y does have a value, and I'm not short-circuiting 1 to 0, and therefore when X is 3, Y is 0. Can you see what gate that would be? X is low, we're high. X is high, we're low. Can you get it? Huh? What do you think? It's a NOT gate. Isn't that cool with just switches? That's pretty cool. We made a NOT gate. So now, we're going to see in these series of lectures, we can one-to-one connect current flowing transistors to a Boolean circuit. And then a truth table. On this beautiful page, this is the last slide before we end this lecture. Let's actually take a look at this. So the idea is, I've got a transistor circuit representation, and I've got a block diagram, and I'm going to say abstractly, all I need to worry about is the block diagram from here out. But if I lifted the hood on that block diagram, I'd see, well, this transistor is doing the right thing, wired a certain way. Let's see if this works. Let's actually take a look and discover the circuit. More complicated circuit. I've got A and B as input and C as output. But also keep in mind, again, we never want to short circuit high to low, and we always want to have C have a value. So let's make sure this is true in all these cases, and let's play with it, okay? So this is, let me get here, make sure, okay, this is a serial line, 2 switches in serial, we said that. And in fact, C only connects when A and B, if this is so let's go back. These are both N-type. These are P-types up here. So when A and B go high, here we go. A and B go high. So that's over here. Only when the A and B go high, only then is C connected to ground. Now, when A and B are high, what happens? Well, this opens up. That opens up. This opens up. And B opens up. Remember, when that goes high, the P-type opens up. So that means C does have a connection to one value. There isn't a connection from C to the 1 up here, to our 3 volts, because both of these are open. There's no way for that ground to get to the 3. So we're okay. We're in this row. So now we're in 1, 1, 0. And watch what happens. The other 3 cases are identical. Watch out. So that's like one set of cases, okay? We only get to that 0 when A and B are both high. The N channel closes, and now C is ground, and both of those guys are open. Now watch this. Here we go. Now all of these are the same category. Watch this. This is really kind of fun. How's this work? Well, if either, in those three cases, we know either A or B or both are 0, which means this is disconnected. Both of these guys are disconnected. That's pretty cool. So there's no connection from C to ground. And this also means that one of these guys, if one or both of them are 0, one of these guys is closed. Remember, when it's a 0, the P-type closes. The N-type opens with a 0. So that means there's going to be a path either here or in here. We saw that kind of parallel guy, which means I don't care, or both. Therefore, C is going to be 1. So in these three cases, C is 1. When either one or both of A are 0, C is 1. And only when both of these are 1, do both of these open up, do both of these open up, both of these open up. Oops, I should draw this better. Both of these open up, both of these open up, no connection, and C routes down there. So this is my output. We're going to see later, this is called a NAND gate. It's like an and says they're only one if both A and output is only one if both A and B, the inputs, are both high. NAND is exactly the opposite. So an AND gate would have been 0, 0, 0, 1. A NAND gate is the opposite of that. So this is why this is a NAND gate. And here is a NAND gate there. That's pretty cool. So we're going to see in this series of lectures how we're going to think about transistor networks and then very quickly move into the block diagram. This is like a building block, call it a NAND, and move forward from there. Once we live in the NAND world, we're now digital and we're not thinking about the transistor anymore. We're kind of abstract. It's below our level of abstraction for the rest of these lectures. That's pretty cool. Also, there's this really interesting fact that by wiring NAND gates together, if you just went to Fry's Electronics and you bought an armful of NAND gates, could you build an AND gate out of a NAND gate? Out of wiring a NAND gate by maybe wiring one of the inputs to 0 or to 1 or to 2 themselves or something like this, could you make an AND? Could you make an OR? Could you make a NOT gate? And the answer is you can. All you need to go to Fry's is to buy a series of NAND gates. That's not the optimal way to do it. And from there you can build AND or NOT, and from AND or NOT you can build everything after that. It's pretty cool. So NAND gate is all you need. It's really very, very neat. So that's kind of a cool thing. So I taught you transistors. I talked about transistors networks, how to treat them as switches, and how to move on to thinking of them as a block diagram, as a digital circuit, has some inputs, has some outputs. We got to make sure the transistors never short circuit. Nothing in the transistor network short circuits, and the output is always connected to at least one or 0, never just kind of floating in the air. So we got that. All that was true for this case, and we're really happy. So, and the next series of lectures, we're going to talk about signals and waveforms. We'll see you there.